Section 4.2 has to do with areas. What we're going to be discovering the area beneath a curve. But really, as we get started with this, all we're really going to do is approximate the area under a curve. And the way we're going to approximate the area under a curve is to use geometric figures, because we do know the area of a triangle, a circle, a square, a rectangle. In fact, the geometric area we're going to use the most is a rectangle. And what we're going to do is break up the area beneath a curve by using rectangles eventually. But the first thing I want to do is talk about sigma notation, because ultimately we're going to be adding a bunch of things together. So sigma notation is a method of adding multiple things together. We use the Greek letter sigma, capital sigma, and we have a little indexer here. Think of it as a little counter from 1 to n. And we add these items, a sub I. Now, I changes, 1, 2, 3, 4, 5, 6, 7, 8, right up to n, and the sigma stands for sum. So sigma notation is a way of adding things together. Think of it as a little summing computer, in fact. It adds a lot of stuff together for us. So, for example, I could do the sum from I equals 1 to 10 of the number 5. Now, 5 doesn't really change, so it's just 5. It's 5 plus 5 plus 5 plus, and it keeps going on, and the last one's also 5. But how many times did we add 5 together? 10 times. So, for adding a constant, it's really just multiplication. And we end up getting 10 5s, or 50. The answer to that would be 50. That leads to our first summation rule. The first summation rule we've got is that when you add a constant together, whatever that constant is, it's simply multiplication, c times n. And so that's exactly what we did just a moment ago. So sigma notation is a method of adding things together, whether they're constants, sometimes they'll be variables, but we add a bunch of stuff together. We like sigma notation because we might have to add hundreds of things together or thousands of things together, and I certainly don't want to write 1,000 terms. So sigma notation allows us to do that without writing all those terms out. What about adding I itself? The letter I itself. Now, I is the actual little counter, and sigma means sum, so the first thing we have is I is equal to 1, plus, sigma means plus, or sum. Next, we click off to the next one, which would be 2, and then we click off to the next one, which would be 3, and all the way up to n. Now, for that one, I wonder if we can come up with a formula like we did for the sum of a constant, a rule, so that we could calculate this very quickly. I mean, we could do one of these, right? We could sum 1 to 3 on the letter I and get the answer 6. But without a rule, we're really stuck when it comes to doing this because we really have to physically write it all out. 1 plus 2 plus 3 plus 4 is 10. I wish there was a formula that allowed us to simply find what this is without having to calculate it manually. Now, there is a formula, and I'm going to show you how to derive that formula. Now, one way of adding 1 through 4 is maybe to represent it with dots. And we're just going to count the dots. There's 1. There's 2 dots. There's the 2. There's my 3 dots. And finally, there's my 4 dots. So we're supposed to add 1, 2, 3, 4, 1 plus 2 plus 3 plus 4, and you just count the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, we don't really need the dots to do that, right? We can add 1 through 4 without that. But something very interesting is happening here. If you look at this carefully, you notice that this is of dimension n, where n is the top of our count This is also of the dimension n. So if I said that the number of dots was equal to n squared, that would be a little bit of an overestimate, wouldn't it? Because you're missing this dot, you're missing these 2 dots, and you're missing these 3 here. So n squared's too much. That would be 4 by 4, 16. That's a little too high. So the first thing we might want to do is just take n squared and literally chop it in half, like that. Now you notice to chop in half these right here, 1, 2, 3, 1, 2, and 1. 1, 2, 3, 4, 5, 6. Like those are all over on this side. There's 1, 2, 3, 4, 5, 6 over there. The middle line, you want half of these dots to go with and half to go without. So by chopping in half, I have to take these 2 with me. So this should be 8. 1, 2, 3, 4, 5, 6, 7, 8. But that's not 10. So the first thing we're going to do is do n by n. Sorry, that's too much. We chop it in half. That's me chopping it in half. But I realize that I'm missing a couple of items here. These 2. These 2 didn't make it into my count. So we got to add them back in. Now, how many need to be added back in? Well, if you look at this diagonal line right here, you notice that there are n dots in that diagonal line. I need to add these 2, which is half of those n dots, back in. The number of dots is n squared plus n over 2. If you factor out the n, it's n plus 1 over 2. And n is just really the top of the count. Does that really work? Well, if n equals 4, let's see what happens. That would be 4 times 5 over 2. 20 over 2 is 10. It does work. So that leads us to this summation formula. If you need to do the sum of I, we can use this newly found summation formula, n plus 1 over 2. Now, we certainly don't need that formula for n equals 4. We can just 1 plus 2 plus 3 plus 4. But what if n was 100? You would have to sit there manually with a calculator and do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus all the way up to plus 100. And then you'll get your ultimate result. What we've just discovered is actually there's a more direct way of getting that answer. I would do 100 times 101 over 2, and we would have the result that way. So there are other summation formulas that we want to make note of. I'm not going to be able to derive these all, but let me summarize the summation formulas for you, and then maybe that will help us determine some of these sums without having to do them manually. The sum of a constant, c plus c plus c, n times, is just c times n. The sum of the letter I from 1 to n, where I is actually changing, we just discovered was n plus 1 over 2. The sum of I squared, again, difficult for me to derive for you, but I will tell you that there is a formula that gets us the sum of I squared. And I can demonstrate that it works on a couple of examples. These are formulas that you definitely want to know. We're going to be using them extensively. What else? How about the sum of I cubed? Sum of I cubed is an interesting one. It's 1 cubed plus 2 cubed plus 3 cubed, but it turns out that it's this formula fully squared. So that would be an n squared, an n plus 1 squared, all over 4. Not a hard formula to remember. If you remember, it's this guy squared right here. That gives us the ability to all of a sudden do a myriad of different sums. So let's try a few. Let's do I equals 1 to 3 on I squared minus I plus 1. Now, this is a sum you can do manually. There's no problems here. Manually means plug I in. 1 squared minus 1 plus 1. That's the first term. Put the 2 in next. 2 squared minus 2 plus 1. Now put the 3 in, and that would be the last one, which is 3 squared minus 3 plus 1. Let's add this all up to see what it is. The first sum is 1. The second sum is 4 minus 2, which is 2. plus 1 is 3. And the last sum is 9 minus 3. 6 plus 1 is 7. The answer better be 11. Now, this is not a big deal as long as n is small. But if the n was equal to 100, we would be here quite some time listing all those terms out. So I wonder if those summation formulas work for n equals 3 and will get me my 11. Let's try to do that with this particular sigma formula. Now, one nice thing about sigmas is the following. And probably put that in parentheses so that sigma applies to all three of them. Sigmas work just like derivatives and antiderivatives. When you have a sum or difference, each term gets its own sigma. You can think of it as almost a distributive law for sigma. It works for derivatives, and it also works for antiderivatives. We do each one separately. They don't really interact with one another. That would be the first thing I would do here, is distribute this sigma to all three of these. So we have the sum, I equals 1 to 3, of I squared, then minus the sum from I equals 1 to 3 of I, plus the sum, I equals 1 to 3 of the number 1. Now, the sum of I squared, we just learned that there's a formula for that. It's n plus 1, 2n plus 1 over 6. For the sum of I, we discovered, in fact, derived a formula, which was n plus 1 over 2. And for the sum of a constant, it's just the constant times the n. And in this case, the constant is 1. So I'm wondering if we're going to get 11 when we run these formulas through. So what we got now is n, which is 3. So 3 here, 4 here, and 7 all over 6. N is 3. So we get 3 and a 4 and a 2. The constant is a 1, and n is 3. So let's see if we can find some way to cancel some of this here. I would cancel the 3 with here and get a 2. I would cancel the 4 and the 2 and get a 2 up there. So that's a 14. This is 3 times 4, which is 12 over 2, which is 6. And this is plus 3. And look what happened. 14 minus 6 is 8, plus 3 is, no surprises, 11. So there's little question that this technique does work, the technique of using the summation formulas. Now, the next thing to investigate, and these are definitely, you should practice your summation. And again, the way to do it is distribute the summation to each individual term. By the way, constant multiples are allowed to be parked out front, just like they are for derivatives and integration. So maybe a quick example of that. How about these two? And this time, let's crank it up a notch so that we never could do this on a calculator manually. This would just take way too long. The 4 and the 3 are allowed to shoot out front, guys. And you get I equals 1 to 50 on the I squared. Here, the 3 is allowed to shoot out front. You get I equals 1 to 50 on an I. And we circle these because we ultimately should arrive at some of these sigma formulas that we know about, which are sum of I squared, I cubed, or sum of a constant. Those are the only ones I really have a formula for right now. We do have formulas for these. If you look it up, the sum of I squared is n plus 1, 2n plus 1 over 6, plus 3 over here, the sum of I. That's the one we actually derived. Looks like that. And n is 50. So it's 4, it's 50, 51. And this 50 times 2, that's 101 right there, all over 6. N is 50, 51 over 2. So now we ought to calculate this and see what it's worth here. So 4 times 50 times 51 times 101, all divided by 6, is equal to 171,700. This one, 3 times 50 times 51 divided by 2 is 3,825. Oftentimes these end up being pretty big. So let's see what the total summation is. Now, if you want to try that on your own, I mean, the best way to add 50 things together is to write a computer program, make a loop, or use a spreadsheet and add it that way. But you will get 175,525 if you truly add all that stuff together manually. So we don't want to add it manually. We now have what I'll call a summing computer, and those are the formulas I just talked about, the summing computers. So now, we switch gears a little bit, and we talk about the area beneath a curve. If I were to produce a function like this, let's pick minus x squared plus 4. Minus x squared plus 4 is an upside-down parabola. A couple things we know about it. 1, 2, 3, and 4. Right here it peaks off at 4. And it's upside-down parabola. In fact, I know the y-intercepts, the x-intercepts, are 2 and minus 2. And I said, could you possibly estimate the area beneath this curve? Now, one gross approximation would be to just draw a rectangle, right? 4 by 2 is 8. So if I drew a 4 by 2 rectangle, you could immediately say that's an over-approximation. 4 times 2 is 8. The area is not 8. I can visually see that it's less than that. But how about we get a more accurate reading on area? What if I said I would like you to slice the area up into, let's say, 4 rectangles? 4 rectangles. Now, I would do that slicing down here. So the first rectangle would be up here. Second rectangle would be here. Third rectangle would be here. And if you look, it creates 1, 2, 3, 4 intervals. This is a half, this is 1, and this is 3 halves. Now, within each interval, it really depends on which endpoint you pick as the y value for your rectangle. You could very well pick this to be your endpoint or y value, the rightmost endpoint for the y value of this rectangle. If you do, you have just created this rectangle. Now, once you decide on picking the right endpoint within an interval, let's do that for all of them. So this next interval, we'll pick the rightmost or lowest y value and make a rectangle. This one here, we'll pick the rightmost and we'll make a rectangle. And then finally, this one here, we'll pick the rightmost, the rightmost y value is 0. So we don't really get a rectangle on that one. Now, to get an approximation, I would add all 4 of these areas up. Area 1, area 2, area 3, and area 4 is 0, but we'll deal with that in a moment. So let's call this the under-approximation of the area beneath this curve. It's approximately equal to A, the real area beneath this curve, but it's an undershoot. What is it? The under-approximation is the sum of all 4 areas. But what are all 4 areas? Each area has a length and a width, or a height and a width. Let's call this the height, and let's call this right here the width. Now I'm going to refer to the width as delta x because it is a delta x. It is a little bit of a change in x down there. And the thing is, I think the first thing, let's go ahead and calculate all of these widths and heights. So let's start with the first one. That would be the height 1 times width 1. And this would be height 1 right here. Plus, the second rectangle. There's a different width down here, but actually it's the same, right? If I put little dots here, you can see that that width right there is the same as this one. So, but the height's different, definitely. Here's the height right here. That's height 2. So it would be height 2 times width 2. And the next one would be right here, height 3. Height 3 times width 3. And then height 4 is way down here. Height 4 is actually 0, but we'll call it height 4 times width 4. Now, it turns out that the way we've sliced this up, all of the widths are the same. That makes the problem a lot easier. And we call these widths delta x. So it turns out that each one of the widths are all the same. They're all delta x. Now, the starting point here is right here at x equals 0, and we're going to refer to that as A. The stopping point is over here at x equals 2, and we'll refer to that as B. So starting point A, 0. Ending point B, 2. So how would you compute delta x, which is the width of each individual slice? I'll do that up here. Delta x is a little bit of width in the x direction, and what it is the master width, b minus a, divided by n, the number of slices. This formula we'll reuse quite a bit, but delta x is b minus a. That's 2 minus a, 0. And how many slices did we make? 1, 2, 3, and I know that one doesn't have any area, but that one would be 4. And it makes perfect sense that delta x is 1/2. Take a look. This is 1/2 wide, and then from 1/2 to 1, another half, and another half, and another half. So delta x is 1/2. But look at this. If I factor out the common delta x, all I really have to do is add my heights together. So the real question is, what are the heights? Now, the thing about this problem is you don't need sigma notation. I guess all you need is delta x, which we already have. You need 4 heights. So where do these 4 heights come from? Well, the 4 heights come from these x values down here. So how do we get this height right here? What is this height? Well, if you come down here and if I label these x values, I'll call this x0. I'll call this x1. I'll call this x2, x3, and the last one is x4. There they are. My x's are lined up pretty nicely now. Guys, how do we get the first y value of this interval? Look at what we did. The f of x1 is right here. That's what it is. It's the y value. It's evaluating your function at that particular x. And remember, we chose the rightmost x. So I guess if I want that height, I would do the f of x1. How are we going to get h2, the height 2? Well, here's height 2 right here, guys. Line it up. How did we get it? Well, we went here to x2 and reached up and got ourselves a y value, x2. That's the f of x2. So I guess we need the f of x2 and the f of x3 and finally the f of x4. So to approximate the area beneath this curve, it ends up being pretty straightforward. A delta x that you can compute fairly simply. Remember, we did that up here. B minus a is the master width, which is 2 units wide, divided by n, the number of slices. That turned out to be 1/2. And all we have to do now is evaluate the function 4 times, 4 different heights. And here they are. So we don't need any fancy sigma notation because I'm only adding 4 things together. But what is x1, x2, x3, x4? Let's go over here and take a look and see if we can figure it out. x1 is right there. It's 1/2. x2 is right there. It's 1. x3 is right here. It's 3/2. x4 is the last one. It's the same as b, and that's just 2. So I know some of the notation is getting a little bit fancy, but all we really did is we calculated the width of each rectangle. We ended up discovering that they're all going to be the same. We call it delta x. It's computed just once as b minus a over n. That part's done. And now you need those y values. And you have to say, how do I get y values? Well, you use the function. But you've got to tell the function where you are. So now I had to figure out what all those x values were at the bottom. And those were all about a half a unit apart, exactly a half unit apart. So one of the problems I see here is that people end up adding 1/2 plus 1 plus 3/2 plus 2. That's not what we need to do here. Don't forget, we got to execute that function. Well, here's the function up here, guys. So it's time to run our function and get our underestimate. So our underestimate should be the 1/2. And now let's really run this function here. Now this will be 4 minus 1/4. That's a half squared. So that's going to be 3 3/4. Plus 1 goes in, 4 minus 1 squared. Plus 3/2 go in. So let's figure out what that's going to be. 3/2 goes in, you're going to get 9/4. This is 16/4, by the way. 16 minus 9 is 7/4. And finally, 2 goes in, 4 minus 2 squared. That's 0. In fact, we remember that, 0. There is no height over there, that last one, right? We already know that from here. So it's flat down here. There is no area that contributes. So let's add all this together. Okay, got my calculator here, and I'm going to add 3 1/4 plus 3 plus 7/4, and then divide that by 2, and the underestimate of this area is 4.25 or 4 1/4. Okay. Now we know that's an underestimate because if you look at the picture here, it's pretty clear that we have missed quite a bit of area. We've missed not only that end piece back here, but all these little white spaces were not accounted for. So we're missing stuff for sure. Therefore, I would call this an underestimate. Now the next thing I'd like to do, I'd like to overshoot it. No sigmas needed. In fact, all we have to do is add 4 areas together. That's all I'm doing. I'm adding 4 rectangular areas together. Let's repeat the process, but this time, when I look at my rectangles, I'm not going to pick the rightmost y value. I'm going to pick the leftmost y value, and I think that will get us an overshoot. So let's see what we can do about that. Same function. Okay, we reach up to 4, and we draw this portion of the parabola like this. Comes down to 2 here. Sorry about that. So we get down to 2, and now we need to slice again. So we slice here, and we slice here, because I'd like n to be equal to 4. And you know what? Let's label this a little better now. This is A. This is also x0, and of course it is 0 itself. This is x1, and it happens to be 1/2. This is x2, and it happens to be 1. Let me circle these x's here. x0, x1, x2. This one would be x3, which happens to be 3/2 circled. And then this is x4, which can also be referred to as b. So I'll block these a's and b's up. So a and b is the beginning and end. x0, 1, 2, 3, and 4. And then the actual number values are in here. What if I went up here and I grabbed the leftmost value? And if I capped it off, you'll notice that I get a little bit of an overshot on my area. Come on over here, grab the leftmost y value, and same thing, I get an overshot over there. Come on over here, grab the leftmost y value, gives me another overestimate, and finally over here, the leftmost y value, and I get an overestimate. Do you notice that I got these little rectangles here that shouldn't be there? These little spaces up here, they really shouldn't be there. So this clearly should give me an overestimate of the area beneath the curve. And realize that all you have to do is add the area of 4 rectangles. We don't need sigma notation or anything like that. And how do you add the area of rectangles? Well, you need length times width or height times width on each one. So what's my overestimate going to be? It's going to be the same thing as before. 4 rectangular areas added together. Each rectangular area has a height and a width. A height and a width. So we need to add 4 of these together. Now remember, the width, luckily, is the same for each one of these. I'll just highlight one of them. This one right here, that's my width. Pull that aside, and actually we refer to the width as delta x, and we always use this formulation for it. It's b minus a over n. So what's our width going to be? Well, b is the end, which is 2. A is the beginning, which is 0 over 4 slices. It's still a half. So we factor out the common width because they're all the same. They're all delta x's. So delta x comes out front, and yet again we have to add 4 heights together. That's where the adding takes place. Now again, we got to figure out how do we get heights, and functions are what get us heights. Functions get us y values, so don't forget you got to execute your function, but where? Well, that requires me to look here at the graph to figure out where should I do this to get my top height. My top height is right there. How did I get it? Come on down here. I did the f of x0. That's the first one. My second height is right here. Where did I get it? Slide down, take a look. You got it from x1. So I think you can extrapolate that we would go, x1, x2, and finally x3. 0, 1, 2, 3. No one even touched x4. All right. This should be an overestimate, by the way. What is x0? Take a look at the picture. x0 is a, it is 0. So I need to do the f of 0. What is x1 here? x1 is the very first x. It's simply 1/2. What is x2? x2 is this x value, which is 1. And then finally x3, which is this x value, which is 3/2. Now, at this stage of the game, I did say be careful and don't forget that you've got to execute your function, right? So let's not forget to execute the function. So our function, just as a reminder, was 4 minus x squared. Let's not forget to actually execute that. So let's see what we got. 1/2. Put the 0 in. That's just 4. Now let's put the 1/2 in. That's 3 3/4. I think we've seen that one before. Put this one in. We get 3. We've seen that one before. And then finally the last one would be 9/4 right here. This is 16/4. 16 minus 9 is 7/4. So let's see what our overestimate will be. Okay, we add this together. What we get is 4 plus 3 3/4, I'm sorry, plus 3 plus 7/4, and then ultimately divide that by 2. So let's talk about what we discovered here. We did 2 different techniques of finding the area beneath the curve. One was an overestimate, one was an underestimate. The overestimate came out to be 6 1/4. The underestimate was 4 1/4. So you could probably get an idea of what the real area should be, probably about 5. So I think right now my best guess for the area beneath this curve, my best guess is the average between the over and undershoot. So we had 4 1/4 and 6 1/4. Let's add them and divide by 2 and see what a good, true estimate of the area beneath the curve would be. Now I will say this. I don't believe that the exact precise area beneath this curve is 5.25. What I do believe is that this is our best guess. How could you make this guess even better? Well, the way to make the guess even better would be to make more slices. Make n equal to 8, make n equal to 16, and so on. That would be the way to make the area even better. So the best you can do right now is average the upper and lower and get your best guess. If you want to make it more accurate, you want to make n bigger and bigger. What will happen to delta x? Delta x becomes smaller and smaller. So that's really the true way to get your best approximation. Now in calculus, we're going to push this even further. Instead of going from n equals 4 and saying, you know, n equals 8 is going to be better, 16, 30 to 100, and then finally delta x gets smaller, a half, a quarter, an eighth, you know, and then finally you're lining these tiny hair-thin rectangles up, and they line up so nicely that we don't get that blockiness across the top, and you get an incredibly accurate result. Calculus allows us to do something pretty amazing, and that is it will allow me to send n to infinity. I'll have an infinite number of rectangles eventually. It will allow me to take delta x and shrink it down to 0. Now, of course, we need limits to do that. But with limits in place and allowing n to go to infinity and allowing delta x to go to 0, we will produce the exact correct answer. Pretty amazing to get the area under this smooth curve precisely and exactly. Right now, all I have is this estimate 5 1/4, which isn't bad. The area could be 5. I'm not sure what it is, but we'll find out as we push a little deeper into this. So for right now, I want you to be able to do over and underestimation of the area beneath the curve. The way to do it, choose a number of rectangles, calculate delta x, b minus a over n, and then pick whether or not you're going to take the left or the right side of each interval. That will tell you where to evaluate your function to get your height in each case. I don't need you to use sigmas for this particular problem. I just need you to add, let's say, 4 heights together. That's all I'm really asking you to do, and you will get both the over and underestimate. Maybe as a last step, you average them together and say, there's my best guess, 5 1/4 for this problem. The next video will dig a lot deeper into this. The next video will say, yes, indeed, I'm going to push this much more towards an exact answer. And the way we're going to do that is we're going to send n to infinity. The number of slices, we're going to send delta x to 0 at the same time. And sure enough, the exact area under the curve will resolve itself. And as we push a little deeper, you're going to find out how well this connects with the antiderivatives that we just did previously. That integration will lead us to that result. Thanks very much. We'll see you in the next video.